Okay, on Zoom. Again, I cannot see your chats, so please speak up if you lose me or something is off with the slides, etc. All right. Okay, we are back. Okay, we are back here today. Sorry for a couple minutes late. I was working on the slides on my other computer. It didn't sync up to Google Drive, so it didn't show up on this computer. So I had to do some acrobatics to get the most recent version. We got about 19 people on Zoom today, and the rest of you are here, and some are not showing up anymore. Surprise exam, no. All right, so we are almost halfway through this chapter. The hardest is yet to come, but your homework assignment is going to be on initial value problems, which are much simpler to deal with because there's also this generic tool called ODEint that you can use. Once we hit boundary value problems, things are going to get a little bit more complicated. Unfortunately, I will not have time to give you a homework assignment on that. So you will have to rely on the examples that we do in class, the analysis that we do in class for the final exam. Okay. But that's where kind of complexity is going to get. We're going to have to combine linear solvers and nonlinear solvers and all of that. We'll see some nonlinear solvers here once we look under the hood of ODEint. So I promised you last time, it's always a challenge in this class, and sorry if I keep kind of beating the drum on that, is trying to balance between just teaching you the tools that you will need when you pursue your career and do your research or engineering versus kind of teaching you the nitty-gritty details. And I'm always trying to balance that. I know some of you really want to get to the nitty-gritty details. Some of you just want to use the tool. So I'm trying to make everyone happy. All right, so today we're going to look under the hood of ODEint, just kind of touching the surface on the theory of time integration methods. Okay, so there are PhDs done on time integration methods. We're just going to touch the surface to explain to you some of the key concepts based on a very simple finite difference method applied to initial value problems. And then we'll talk a little bit about stability and look at implicit methods, and then call it a day for initial value problems. Okay, not call it a day on the lecture because I think we have time to start on the boundary value problems. Okay, so the simplest type of integration is what we call explicit time integration. That doesn't mean anything yet because we haven't defined what we mean by the word explicit, but it will make sense once we see the result of the equation. So far, we have been dealing with an initial value problem, the first order ODE, d phi by dt equals some right-hand side. That's a function of time, the dependent variable, and the independent variable, and the dependent variable itself. So right-hand sides could be h times phi minus phi infinity, like the temperature problem. It could have time in it. That's fine. Now, why do we always focus with initial value problems on first order ODEs? Because you can turn any second or third or fourth order ODE into a system of first order ODEs. Just call phi prime v, and then phi double prime becomes v prime, and then phi triple prime becomes w prime, etc. So that's how all initial value problems can be presented as whatever order your ODE is, you can turn it into a system of first order ODEs. We saw an example of that when early on in these slides. Okay, so now assuming that you know how to do that, you got to the single ODE or system of ODEs. This is the problem we're facing. We have a dependent variable, dependent quantity phi. We're calling it from now on d phi by dt equals some right-hand side forcing function of t and phi. You are given an initial condition, phi at t0 equal phi 0. Okay, that's, that value that's given to you. And you are to integrate to solve this problem from some arbitrary initial time to some arbitrary end time. Okay. So with the lobster, for example, we started from 0 to 60 minutes or 20 minutes, and the initial condition on the lobster was its temperature, right? Because you were solving phi was the temperature in that case. Now, the first step, so pictorially, what this looks like is that if you imagine you are trying to find the solution for phi as a function of time, if you look at the axis of time starting from t0, where you know phi0, then your objective is to find this red curve. Okay, we do not know this red curve yet. All we know is that the slope of the red curve, d phi by dt, equals something. That's a function of phi, so that kind of makes it a kind of tautological problem. So our objective is to try to untangle that, okay, with the time integration procedure. So the first step that we're going to do discretely is to divide this time line into discrete points, like we did with the Lin space, like we did with the heat transfer problem at the beginning of the semester. So we're going to dissect this, discretize this into a series of points. We'll assume here we have constant spacing. You can call it h or delta t to designate the size, the time step. We call this the time step. Okay, so you can take, let's say you want 100 time steps, you divide this into 100 intervals. Okay, you want 200 time steps, you divide this into 200 intervals, and from that you can deduce your time step size. Now you assign, okay, for each one of those discrete points, these yellow points here, you assign a time value starting from t0. T1 is t0 plus delta t, t2 is t1 plus delta t, and so on all the way to t end. Okay. Now numerically, then our objective would be, rather than finding this continuous red curve, our objective would be to find those discrete values on the red curve that correspond to the discrete times that that we have identified. Okay, we haven't done anything so far except kind of just define a few things. So I'm going to shrink this together and put, you know, phi0 at t0, phi1 at t1, and then phi n at tn, right? So those are the discrete values that we are trying to compute. What you know is phi0. What you do not know are all the other phis. Okay. Now we're going to use the ODE itself and the initial condition to develop a recipe to move from phi0 to phi1, and then move from phi1 to phi2, and so on. Okay, using the governing equation. We only have two pieces of information: the initial condition and the governing equation itself, the ordinary differential equation. Okay. Now, I want to make a very important statement here, which might be obvious, but it is important in the discussion, is that this ODE is valid for any time t, right? So over this time interval, t0 to t end, excuse me, assuming, you know, everything is physical, everything, all the derivations are correct, this equation is valid in this interval going from t0 to t end, right? So what I mean by it's valid is you can take that ODE and evaluate it, evaluate the derivative, evaluate the right-hand side at any time t in that interval, okay? And that also means that this ODE is also valid at any one of those discrete points. So you can take that ODE and evaluate it at any one of those discrete points. So keep that in mind. Now, because we only know the initial value phi0, I want to pause it and say, you know what, let's start by evaluating the ODE at phi0, because we have one piece of information there that we don't have anywhere else. Right? So I'm going to take that ODE and apply it at t0. So that gives me d phi by dt at t0, agreed? That's what I mean by applying the ODE at t0, equal the right-hand side at t0 and phi0. Agreed? So we know t0, we know phi0. We don't know this yet. Okay? So we're almost there. Now the next step is to try to use this equation to infer a formula for phi1 using phi0. Can you think of anything that we can do to obtain some relation for phi1? Kimball.
Well, the derivative should give you an approximate slope, so you can just use that to make a line.
To the next point. So a line, or yeah, just so how, what would that be in this case?
So
Do you remember?
You would put the derivative and then
How can I express that in terms of phi1?
So you'd be like B1 is equal to
Or what is the derivative in terms of, you are correct. So what is the derivative?
the R of T naught B naught times the delta, the H plus B.
That's correct. That's the formula for phi1. But what is the formula for d phi by dt?
Oh, it's whatever you defined it as, right?
Okay, so what Kimball is saying is we approximate the derivative. And we learned how to do that in the finite difference chapter, right? When we learned to differentiate, approximate d phi by dx, right? So you remember that formula, forward difference, for example. So if we were to use the forward difference here, that d phi by dt is nothing else but the definition of the derivative, which is phi1 minus phi0 over your distance, the spacing between the 2 points. Remember that? And that was a first order approximation. So d phi by dt at t0 is phi1 minus phi0 over h. That's the forward Euler method, right? The forward difference method, sorry, forward difference method. And it incurs an error of h, which is a first order error. So now when you look at this, you're like, well, I know h, I know phi0, I know r because that's given to you. It's whatever the right-hand side is. And you know t0 and phi0. So you know everything except phi1. And you can simply solve for phi1 algebraically, right? So if you do this now, you substitute d phi by dt by this approximation, phi1 minus phi0 over h. That's approximately equal to r of t0 phi0. Then you can simply solve for phi1. And that gives you what Kimball said, phi1 equal phi0 plus h or delta t times the right-hand side at t0 and phi0. That's kind of pretty simple, right? Now, that's why we call this method an explicit method. It's because for every value, you can solve for that value algebraically directly. We will see later that other methods will require to solve a nonlinear equation for phi1 and phi2 and phi3. But with explicit methods, because everything on the right-hand side is known, you can just simply solve for phi1 algebraically. You can just pull out phi1 to the left-hand side. Now, the same thing applies for all the other points. So if you think of this now, at t0, you have phi0. At t1, which is t0 plus h, you have phi1 equal phi0 plus h times r t0 phi0. Now, go ahead and solve for phi2 in terms of phi1, phi3 in terms of phi2, and all the way to phi n. Just write down the formulas. So you can either go back to the ODE itself and say, I'm going to evaluate d phi by dt at t1 and apply the forward Euler, the forward difference method, and so on. Or you can just infer this from the formula. Yep. Give you another minute. Most of you got it. Kind of pretty straightforward. Maybe that's why it's called the forward Euler. The straightforward Euler method. Sorry for the, can't stop myself from doing puns. It's very empowering when you do puns in another language, right? That's not your kind of primary language. You feel like so powerful. My first pun Like I had been like for 2 years in the US, and I came up with this hilarious pun joke, and everyone congratulated me. I'm not going to say the pun joke, maybe off the record at the end of the semester, but it was a very dumb pun joke. Anyway, so okay, so you can simply recursively build this out, right? Or just apply that forward difference formula that we applied at each point. And so phi2 at t2, phi2 is phi1 plus h times right-hand side at t1 and phi1, right? So the value at the new point has to do with everything at the previous point, okay? Has nothing to do with any information from the new point, okay? And that's why this formula is called an explicit method. And in general, we say that when you apply, I don't know why this is kind of weird today, but in general, to apply, you see some of the formulas are off the screen. But in general, when you apply this method to an ODE of the form d phi by dt, let me see if I can fix that here, move these a little bit to the side, okay? If you apply this formula to a d phi by dt equal right-hand side with an initial condition phi 0, this is called the forward Euler method, okay? Because you're using a forward difference to approximate the first derivative, okay? It's called the forward Euler method. It's given by the formula phi n plus 1 equal phi n plus delta t times right-hand side at n, okay? You will see oftentimes I write it as r sub n. It means that all the right-hand side is evaluated at quantities at n. What does n and n plus 1 mean? N plus 1 is your new time, n is your previous time. You know everything at n, okay? So starting with n equals 0, you know everything at 0. You evaluate at n plus 1, which is phi 1, and so on and so forth, okay? And that's the forward Euler method. Algorithm is very simple. Given phi n, t n, phi 0, phi 0, t, or phi n, I guess, t 0 and on the right-hand side, you can start your time counter. Tn plus 1 is Tn plus delta t. You evaluate your phi n plus 1. You update your time, and then you keep looping, okay? I'll show you the code for this in a minute. I want to bring back this Hidden Figures film. So I don't know if you will be able to hear it, but if you haven't watched it, I don't know if it's still on Netflix, but okay. So Dorothy.
Is when the capsule moves from an elliptical orbit to a parabolical.
Yeah.
There's no mathematical formula.
Well, there is.
Calculate launch and landing, but without this conversion, the capsule stays in orbit. You can't bring it back home.
Maybe we've been thinking about this all along.
How's that?
It's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependent.
That's right.
It is.
Euler's
Euler's
method.
method.
That's ancient.
Stay in the Big Bang Theory, Cooper. So, right. Now, technically, I don't think there's been a debate on some forums whether they're talking about actually time integration with the forward Euler method or something else that has to do with another thing called the Euler method, okay? So it's been a debate, but nonetheless, I like to use this example to, impress on you that, the Euler method is a big deal. It's never ancient math. It's still in use today. We use it in our code. So, it's a pretty powerful technique. And so she was able to get the capsule in orbit, using the Euler method. So maybe you will use it one day and put someone in orbit and send me an email, say, yay, did this. Anyway. All right, so let's turn the lights off. let's do an example so that you can just kind of exercise your hand a little bit. So we're going to take this this ODE, d phi by dt equal minus t squared phi to the power 4. Okay. And with an initial condition phi 0 equal 1. Now you see the right hand side is both a function of time and of the dependent variable itself. So it's a function of the independent and the dependent variable. Okay. And you have the initial condition phi 0 equal 1. And we're starting from t0 to some arbitrary time t end. And I'm asking you to take a time step of 0.5 seconds. And therefore, your t1 is 0.5, t2 is 1, t3 is 1.5, and so on. Okay. And this is the forward Euler formula. The first step is to express the right-hand side in the forward Euler formula to use the actual right-hand side given in the equation itself. So go ahead and just simply substitute the right-hand side of the governing equation into the other governing equation, the forward Euler formula. So instead of r of t n phi n, put in the right-hand side that's given to you in terms of t n and phi n. So substitute the formula, not an actual time, right? So we need just the generic formula, okay? So if that wasn't clear, what I mean by this is simply taking the right-hand side, t squared phi to the 4 minus t squared phi to the 4, putting it right here and multiplying by your time step size, which is 0.5, okay? So now that's the formula we're gonna be working with, okay? Phi n plus 1 equal phi n plus 0.5 times minus t n squared times phi n to the 4, okay? So now you're going to do some actual number crunching. Starting with phi 0 equal 1, go ahead and calculate phi at t1, which is phi 1, okay? Using that formula, I'm sorry that it's outside of the screen. I don't know what's going on with the projector today. You better get used to this because, you know, this is an exam problem, okay? You need to do this because it gets confusing. Like, which t value do you use? Do you use t1 or t0? Do you use phi 0 or phi 1? So it's really just algebraic work. If you're done with phi 1, go after phi 2. Okay. So Alicia has phi 1 equal 1, and I'm going to agree with that. Okay. So phi 1 is phi 0 minus h times t0 squared times phi 0 to the 4. Then you simply substitute numbers. H is 0.5, t0 is 0, and phi 0 and 1. So that gives you 0. So that gives you a total of phi 1 equal 1. Let's go ahead and go after phi 2. And let me just move that formula to the center. Did Maxine take your calculator again? You got your own. Okay. All right, phi 2. What did you get? 0.875, right? That's the formula. So, I leave this for you to continue at home and double check your values. So do this exercise at home. Make sure you get the numbers correctly, because there are so many ways to mess this up. Okay, if you get the wrong t, okay, or the wrong phi value on the right hand side, you can mess this up. Okay. All right, so let's go ahead and Pythonify this thing. I want you to think about a pseudocode to how we would implement the forward Euler routine in Python. And specifically, what arguments does the routine require? Don't worry about passing additional parameters to the right-hand side. We'll worry about that later, like we did with ODEint. Remember, we wanted to pass the advective heat transfer coefficient and the mass, etc. Don't worry about that. Just worry about, given in ODE, how would you, what arguments do you need, does a forward Euler routine need at a minimum? That's the formula. And what would your routine return? Okay. Think about that. It's a group discussion. And again, these answers are generally open-ended, right? Because we each could implement this differently. Like someone might pass a time array, someone else might pass a time step size and a t0 and t end, right? So that's up to you. I gave you like half of the arguments. The group energy is not, the force is not with the classroom today. That's okay. We're all kind of winding down for the semester. All right, let's see, we got any takers? Let's start with this column over here. Go ahead.
So we want our ODE itself.
What specifically do you mean by the ODE itself?
Just our first order differential equation.
Okay, so could we pass an ODE? What do you mean by passing the ODE? Like, do I pass d phi by dt equal right-hand side? Like, what am I passing to it?
You could like define your d phi dt equals right-hand side in the second function.
Yeah, so we pass the right-hand side because the routine is solving d phi by dt anyway, right? So when you say passing the ODE, you're specifically talking about passing the forcing function right-hand side. Okay, good. So we need the right-hand side, and that is just the name of the routine that you would implement. Okay, so let me take it from another group, if that's okay. Let's see this column. Alicia and Brian, you had a heated discussion.
We were talking about how we would want to return an array of all the values.
Okay, that's correct. So you jump to the second question, but that's right. Yeah, that's correct. I'll take that as an answer. So at least your routine needs to return all the solutions, right? The solution values, phi 0, phi 1, etc. That's great. Okay, so let's see from this column. No thoughts on arguments that we want to pass? All right, Kimball?
You need a step size.
Okay, so you need a step size. Rich? That's what Maxime, yeah, that's what we need. We at least need the right-hand side, okay? Now the time step size, could it be option, for the time step size to work, what else do you need? t end and a t0 as well, right? So if you wanted to pass a time step size, you would need a t0 and a t end, and inside the routine, you would negotiate how many time steps you need, right? Or you would start from t0 plus delta t until you reach t end or higher. What's an alternative option to passing a time step size? Yeah, so a lin space. So Alicia's saying we, instead of passing t0, t end, and a time step size, we could do that above the, when we're working with the ODE itself, outside the routine, and instead just pass a lin space like we did with ODEint. Okay, and then within the lin, and then you take the lin space, it starts from z0, ends at t end, and it could have any time stepping really in between, right? So you could have equal spacing, or maybe somehow you create an array that's not a lin space, but with different time steps. But then as you're looping, you got to pick up the correct time step. Here, we're just going to be focused on equal time step size, so I'm not going to worry about variable time stepping. So we would at least need the right-hand side, either a lin space or an array for the times at which we want to find the solution, or t0, t end, and the time step size. What else? So there's one more thing that is really necessary. Yes, thank you. So we would need phi0, the initial condition. Without the initial condition, we do not know where we would start, right? Okay. So now we jump to the return. So Ryan said, at a minimum, we need to return the solutions, right? Phi0, phi1, phi2, all the way to phi n, phi tn. Could we return something else? Maybe, I don't know. I mean, we haven't spoken about error yet, because it's really hard to assess error in this method. We know that the error is bounded by delta t, right? It's order h. That's the best we could know. But to get kind of a clear estimate of what the error is, there's no like one formula to do that. We would have to solve the same problem, but with a smaller time step size, and take the difference between the two solutions and look at how that difference changes as we shrink the time step size. It becomes more complicated than I want to teach in this class. So I'm not going to worry about the errors, but in other methods, we were returning the error as well, a number of iterations. Here, you don't have a number of iterations because you're just moving as many time steps as you have. Okay. So that's how I would do it. That's one way. Define forward Euler method. Okay. Takes a right-hand side initial condition and a time array. Inside the routine itself, and I had asked you to create a pseudocode, but we'll just do it together. I would create an array f for the solution, okay? Initialize, and that array is of the same size as how many time steps you have, right? Because that array is going to contain phi0, phi1, all the way to phi n. And then I'm going to initialize that array with the initial value, phi0, and then loop over all the time steps and update. Say f literally like this, fn plus 1 equal fn plus delta t times right-hand side of fn and tn, or tn and fn, and then you return. Okay. So this is one version of the algorithm. Define forward Euler, gives it right-hand side f0 and t. And then this is a reminder of the formula that fn plus 1 is fn plus dt times right-hand side. First, I grab the number of steps, which is the length of the time array. Okay, so how many points do you have in that time array? And then I calculate my time step size. I deduce it from the difference between any 2 points in this time array. Now here, I'm assuming that the time step size is constant. If it's not constant, you need to do something else. You cannot just do this. You would need to infer delta t further down. Then I create an array for the solution, and I fill it with zeros, and it's of the same size as the number of time steps you have. I initialize the first entry in my solution. So this f is going to contain phi0, phi1, phi2, and so on. So the first entry in f is simply f0. And then I start looping, going over all the time steps. For each time step, for n in the number of time steps, fn plus 1, look at how cool this is. It's very expressive. It looks exactly like the formula. F at n plus 1 equal f at n plus delta t times right-hand side evaluated at f at n and t at n. Now here, you got to be careful. If someone defined the right-hand side taking T and then F as the arguments, you got to make sure that you swap those here, right? So make sure you use the right-hand side here the way you intend to use it. If you over here, I'm deciding that my right-hand side always looks like right-hand side of phi comma T. Someone could say, no, right-hand side should look like right-hand side T comma phi. Then you make sure you swap these arguments here correctly, okay? The other version, I don't know what this is doing here. Okay. The other form, which is what Kimball suggested, is going from, I didn't put T0 here because I assumed T0 equals 0. But ideally, you would give T0, T end, and a time step size. And then in here, you would infer the number of time steps that are needed by essentially taking T end over delta T. This might not come up to an integer number, okay? But then you're not going to end exactly at T end, okay? So you might end one below it or one above it, you know, but that becomes more of a kind of little nuance, okay? So let's go ahead and go back to our lobster example. Remember the lobster example with gaps notebook. If you keep scrolling down, there's a built-in forward Euler routine that we're going to use to try to solve the heat transfer problem to the lobster, okay? On Zoom, would you mind please muting yourselves? All right, so I remember as we did all of this. Yeah, okay. So you see there's a section called using our own integrator. So I'm going to go ahead and reevaluate this. Kind of remember what we were doing. Okay. Parameters to the right-hand side, etc. And then using our own integrator here, I've implemented the forward Euler method, but note that right-hand side over here is applying F and T. So I want to make sure that my right-hand side is, yep, so my right-hand side is correct. It is declared as taking the dependent variable and then the independent variable in that order. So it's just going to work right out of the box. So you just execute this cell. So let's go over here. Again, here with T end, 20 minutes. And I am over here, I'm going to create a time array with a time step size of 10 seconds. Okay. And the way I do this, I declare dt, I create number of time steps, and then I create the lint space. My initial condition is 311. Okay. And then I solve it using forward Euler, which is this method. I'm going to pass right-hand side convection to get the convection solution. Going to give it the initial condition T0 and the time array. Okay. Same thing for T radiation. And if you execute this and you run it, this is what you get. So if you remember, this is, so let me make sure we got the parameters right for this RHS over here. Okay. So RHS convection, RHS radiation. Yep, that's what we got from ODEint, right? And that's what we got from our own integrator, okay? And it's just gonna work if you change your, you know, I'm not gonna go back over the physics, but let's say you're changing the heat transfer coefficient for the convection case. Let's say you go to 100. So faster boiling or heating with the fluid. Okay, then we should see that blue curve go up faster. And indeed, it does what it's advertised to do. Okay. it just works. You're welcome to dig in the algorithm, the routine, change it. Okay. So now I'm going to do something a little kind of exploratory. I'm going to make my time step equal 100. Okay. And let's see if it's working. Oh, okay, it's going to work. I'm going to go now, make my time step, let's say 400. Whoa. When I put my time step equal for 400, it got really messed up, right? At least for the boiling Mr. Lobster case. Right, so if I go to 350, let's say, well, yeah, it looks like something is off and it's kind of really missing that, you know, it's going negative over here, right? It's going negative over here, which is like super weird because why would, you know, it shouldn't get a negative temperature. So I'm going to run this for a longer time. I'm going to go for 60 minutes. Okay. Oh, look at that. Pardon me?
It's below absolute zero.
Yeah. It's kind of very magical.
That makes sense.
Yeah. It's a magical lobster from the multiverse. It does. So there's a problem, right? Because there was a time step, guess beyond which we couldn't get any kind of physical solutions, right? The other one seems to be just kind of running fine, but you know, if I go back to 100 seconds for the time step, it still looks okay. But then there's a threshold beyond which, you know, our solution became incorrect. We didn't see that with ODEint because ODEint has some magic inside of it. That's going to be what I'm going to talk about next. Okay. So let's motivated by this challenge. Okay. The next few slides, before I talk about the next few slides contain an example of applying the forward Euler method to a system of equations. Okay. I'm not going to go over it in class. It's just algebra. But essentially, I would like you to at least cover this at home, cover this example at home. It's the same thing that we did with the single equation, except you have to do it for 3 equations concurrently. Okay. So it's got the detailed, all the detailed numbers. It takes a single time step and shows you what the numbers are. So please do this. Please work through this example. Okay. As if you're doing it here in class. Okay, so now to motivate you to kind of dig in deeper into what was going on with, as we changed the time step, the solution for the lobster boiling was problematic. The other one is probably also going to be problematic after a certain time step size occurs. I want you to go ahead and download motivation for implicit methods with gaps, okay? And that problem, and what you will be solving in that case is this problem. It's d phi by dt equal minus 1,000 phi, okay? Minus 1,000 phi, with an initial condition of phi 0 equal 1. The exact solution looks like this, okay? It decreases exponentially in a very short period of time, and then just kind of chills out for the rest. Okay. These types of problems are called stiff problems because they exhibit what we call behavior over different time scales. In other words, this ODE contains behavior that occurs at a very fast scale, at a very fast time over here, and then over a very long time over here. And it turns out that explicit methods have trouble figuring out how to solve problems like this, stiff problems. All right, so go ahead and download the motivation for implicit methods with gaps. And then inside that notebook, there is the forward Euler method already built in. Everything is set up for you. And then go ahead and solve the ODE. It's just everything is self-descriptive. Okay. Try to solve this ODE d phi by dt equal minus 1,000 phi. Okay, with a few different time step sizes. Okay, start with a time step size of 0.03. Okay, and then start changing your time step size. Okay, play around with it, just like we did for the lobster. Change your time step size, and let's see what happens. So start with delta t equals 0.003, okay? And then increase it or decrease it, and let's see what happens. I don't know if it has gaps, that notebook. It might have a few gaps. So let me help you fill those out. So here's my notebook. You should be seeing something similar. Okay. So again, first is boilerplate, and then this is the ODE that we're solving. I'm defining this right-hand side for the sharp transient is minus 1,000 phi. Okay. And this is the exact solution, okay, that I've shown you just on the slides. All right, so using the forward Euler method, this is the forward Euler method. In this case, I want to pass delta t to the routine because it's just faster to do that because I want to manipulate delta t. So over here, you're seeing the second version of the forward Euler routine. It's already implemented in there for you. So you run it, and we start here with a initial condition of 1.1 and a t end of 0.1. I'm going to start with a time step 0.003. Okay, I'm not going to save the figure. And then if you run it, this is what you get. Right, so you immediately, I hope you're seeing this. The blue line should contain the exact solution, but we can't even see the vertical line coming because it's just, this becomes very oscillatory. And look at the values over here, 10 to the power 9. Okay. 10 to the power 9. So it's clearly is returning junk. Okay. Now, obviously, if I go for a higher time step, it's going to get worse. So if I go to 0.04, it's actually 10 to the power 11. Then goes 0 to 0.5, it's even worse, goes negative. Okay. So now let's maybe go to 0.002. Oh, look at that. It's bounded by -1 and 1, but it's quite oscillatory, right? It's just jumping from positive to negative, right? So it's clearly not the right solution. But then you go to 0.01, and finally you get something that is okay, right? It starts at 1 as expected, and then drops down to 0, and then just kind of stays at 0. It clearly misses this transition region over here. Okay. So to capture this, you really, to get this right, you really need to capture the behavior that occurs the fastest. In other words, to be able to resolve this curve, you really need, this is the limiting case over here, the behavior that happens in such a small time, okay, which is even less than 0.001 seconds. Okay, so you really need to capture this. In order, capturing the rest is okay, because if you put a time step size of 10 to the -5, which is very, very small over here, you'll be able to capture this, but also this as well, because this occurs on such a larger, what we call time scale. So let's try that. So let's go ahead and try an even smaller time step. Indeed, when you go to a very small time step, you capture all of that. Okay, correctly. Now, intuitively and physically, and what you will learn as you go through your engineering education is you'll learn the concept about time and length scales or scales. Okay, this is a problem that has two time scales. Okay, the first time scale is the behavior of the solution in this very short period of time over here. It drops down in a fraction of a second, and then it cruises along over the rest of the time. So there are two dominant time scales in this problem. And the fastest time scale is going to dictate how well explicit methods are going to be able to solve the problem. But this is kind of a guessing game over here. We've like tried this time step, it didn't work, then tried to reduce it. Is there kind of reasoning behind this? Can we rationalize this? And turns out, yeah, we can reason around it and figure out how to compute a stable time step. But the world of trying to understand how to pick a time step becomes way beyond what we want to deal with in this class. But let me show you some reasoning behind what is going on in this problem. Okay. And this problem was designed in such a way to create these kinds of instabilities on purpose. Okay. Okay. So these are kind of the answers, and the smaller the time step, the more you can capture. Okay, so I'm going to give you now a basic explanation of what is going on. This is an ODE, d phi by dt equal minus a phi. So like the example we gave, minus 1,000 phi. Okay, and phi at 0 is phi 0. This is kind of the setup that I'm going to be dealing with. Okay, now what I expect from this ODE, okay, is for it to be strictly kind of decreasing. So all the values that I want to calculate, phi n plus 1, phi 2, phi 3, phi 4, should all be smaller than the previous value because it has a negative slope. Okay, and it starts with a 0, with a positive value. And this is the formula for the forward Euler method. Phi n plus 1 equal phi n minus h times a times phi n, phi to the power n. A is just that coefficient that we put on the right-hand side. And this is just a way to kind of try to reason behind what's happening in that problem. So now you can combine the right-hand side and write it as phi n plus 1 equal 1 minus ha times phi n. Okay. Now for stability, we say that we want phi n plus 1 to be less than phi n. Okay, for these kinds of problems, because they should be strictly decreasing. Okay. Otherwise, you don't know what solution you're going to get to. You're going to go out of bounds. Okay, if it's always less than phi n, you're probably just going to go to 0 or asymptote to a specific value. So for phi n plus 1 to be less than phi n, then that implies that 1 minus h times a is less than 1. Remember, h is the time step size. That's what we're after in absolute value. Now, for this to be less than 1, this implies that h should be strictly less than or equal to 2 over a. All values below 2 over a are going to return a stable solution. Values above 2 over a are going to return unstable solutions. So now go back to your Jupyter notebook. Okay, and let's see if we pick a one moment. Okay, if we go back to this notebook and look, I have this commented out over here. Okay, 2 over a, and remember a was defined way up here as equal to 1,000. Okay, so if I do 2 over a, that's just kind of borderline on stability. Well, it kind of was still unstable. Okay, so if I shrink that by a little bit more, so if I cut that by half, cut 2 over a by half, then it's going to give me a stable solution, or even take 90% of it. It's probably going to be kind of stable, but it's still oscillatory, but it is stable. Okay, so strictly, the strict meaning of this h over a and 2 over a, I feel like I'm kind of going beyond. So this solution is unphysical, okay, but it is stable because it doesn't blow up. It doesn't go to infinity. Okay, it is unphysical. We call it oscillatory, but the question we answered in the slide is only for stability, for the solution not to blow up. Okay, but still the solution is unphysical, so we need to even cut that time step even by more to get a physical solution. And that's really annoying. That's a really annoying problem to deal with. And that's the problem with all explicit methods. They all have stability limitations. And even if you're stable, you might be unphysical. You might get oscillatory solutions. Okay, so you have to cut your time steps even by more. All right. So let's see if we can find a solution to this dilemma. here come implicit methods. Implicit methods circumvent this problem by using information from the future. What does that mean? Back to the future. Huh? So imagine you're driving your car and looking only in the rear view mirror. You're going to crash, right? Because you cannot see ahead of you. That's what the forward Euler method is doing. It's telling you your new location, phi1, only depends if you're looking at the rear view mirror, phi0 and r0. And that's why we have these problems with stability. Okay, unless you drive very, very slowly, okay, you're probably going to crash your car. Okay, maybe even if you drive slowly, you'll crash it. Don't do this at home. Okay, all right. So with explicit methods, we evaluated the derivative at n, okay, and used the forward difference for the derivative, okay, and then we obtained phi n plus 1 minus phi n over delta t equal r phi n r at n. With implicit methods, instead, you evaluate the derivative at n plus 1. So you do d phi by dt at n plus 1 equal r of t n plus 1 phi n plus 1. And then for the difference, you do a backward difference. So that becomes your this phi, d phi by dt at phi n becomes phi n plus 1 minus phi n over delta t, okay, equal to r to the right hand side at n plus 1. So while you might not see the huge differences between the two formulas, they are very significant. Okay, this one is called the backward Euler method because it's using the backward difference. It's using the backward difference formula. Okay, while at first sight you're like, well, they look the same, right? Phi n plus 1 minus phi n over delta t, phi n plus 1 delta t. But look at the right hand side. This right hand side is at n plus 1. This right hand side at n. So now, let's do this. So now you can think like you can pull out phi n plus 1 from the solution. Okay. I want to do a little exercise with you. Now show that for the backward difference, for the backward Euler method, solve the ODE d phi by dt equal minus a phi. So your right hand side is minus a phi, right? And try to find the stability for that using whatever I used in the previous example. So pull up your slides. Okay, so this is the formula for the backward Euler. Okay, so I'll show you. This is the formula for the backward Euler. Now find the condition on H such that phi n plus 1 is less than phi n. There are huge differences between the two methods. We haven't even said anything about that. But first, I want to show you that. Just want you to try to derive stability for the backward Euler method on this example. D phi by dt equal minus a phi. Okay, that's the formula for the backward Euler. Go ahead and find me a value for H such that phi n plus 1 is less than or equal to phi n. In absolute value. Remember, H is always a positive quantity because it's time step, delta t. The condition needs to be that n plus 1 is less than phi n. So I wouldn't write it that way. Okay, so you need to infer the condition on the coefficient. Okay, so express phi n plus 1 in terms of phi n and try to derive a condition on H. have a typo. You have a typo here, right? 1. You have a 1. Bless you. Okay, Evan got an answer. So what was your answer, Evan?
I just saw the slides really.
Oh, well, I appreciate your honesty. Anyone got any leads through this? Okay. I know you're all exhausted and kind of mentally kind of drained by the end of the semester. If you write phi n plus 1, in terms of phi n, you get some coefficient 1 over 1 plus HA times phi n. Just straight out of the box, just looking at this, you know that the only condition for phi n plus 1 to be less than or equal to phi n is for the denominator to be greater than or equal to 1, right? If the denominator is 1, you get phi n plus 1 equal phi n. If the denominator, okay, if the denominator is 2 or 3, you're always phi n plus 1 is always less than phi n. Okay, so the condition is that, well, because the denominator is always 1 plus something, then it's the denominator is always greater than 1. Right? It's 1 plus a positive quantity, right? Because H is positive and A is positive. And so the only condition for this to work is for H to be positive. But by definition, H is positive because it's the time step. And that tells you that this method is always stable. Whatever time step you choose, you are always stable. We call that unconditionally stable. So that's the power of implicit methods, using information from the future, is that you do not have restrictions on stability. You still have restrictions on oscillations and getting an accurate solution, but at least you're not worried about shooting in the dark for what time step size to use, okay, like in explicit methods. So visually, the forward Euler method is using the slope at phi n, and the backward Euler is using the slope at phi n plus 1. It's kind of looking into the future. But there's a huge difference between the forward Euler method and the backward Euler method. Can you spot that difference? So that difference has to do with the fact that the right-hand side is a function of the left-hand side. So what does that mean? Okay, but in terms of things that we learned, right? So you're right, you're in a loop, but what does that mean? Like, what kind of equation does that give rise to? Rich? Why? Yeah. Yeah, so what if your right-hand side was equal to cosine phi? So you'd have phi n plus 1 equals something that you know, plus cosine phi n plus 1. That's a nonlinear equation. That's x equals something plus cosine x. So in general, the fact that the right-hand side is a function of the left-hand side makes this, in general, a nonlinear equation. Generically, in all cases. Only when the right-hand side is linear, then you can deduce a linear solution. But in general, that's the price you pay for implicit methods. Okay? In that, at every time step, every time you're trying to move to phi 1, to phi 2, to phi 3, you have to solve a nonlinear equation. And if you had a system of those, you'd have to be solving a system of nonlinear equations. And we all know how annoying that was, right? And how painful that is, okay? So that's the price you pay when you are doing implicit methods. So then for each time step, you have to define a residual function, which is the left-hand side minus the right-hand side. So your residual function, g phi n plus 1, or r, is phi n plus 1 minus phi n minus hr at n plus 1, human resource, HR equal to 0. Sorry. I've been dealing with HR recently, so it's like this is the last place I want to see HR. Okay, so it is a nonlinear. Every time step you're doing is a nonlinear equation. Okay, and that is the price you pay for implicit methods. Okay, so an algorithm then for the backward Euler, and I have that implemented in your notebook. We're not going to spend time on that, but I'll just give you like one example in the next slide. But essentially, you follow the same procedure for the forward Euler method, except that once you want to solve for n+1, for phi n+1, you have to call fsolve, or the bisection method, or whatever algorithm you've implemented, just to get phi n+1. Okay? So here's an example from kinetics. dc by dt equal minus kc squared, with an initial condition c at t0 equals c0. Okay, that's the initial condition. I want to use the backward Euler method on this, an implicit method. Therefore, Cn+1 minus Cn over delta t equal minus k Cn+1 squared. Now that's a quadratic, right? You could probably solve this just using the formula for the quadratic, but it just kind of illustrates the point that this is a nonlinear equation. Okay, it is a nonlinear equation that you have to find the root for. Then you define your residual essentially by taking the left-hand side minus right-hand side, right-hand side minus left-hand side. Then you can either do a numerical so you can do here an analytic derivative, okay, g prime with respect to Cn+1. Remember, you're solving for Cn+1, and you can just do a Newton solver, okay, to iterate. So within every time step, you have a Newton solver iteration. Okay, that's what ODEint internally is using, a very complex algorithm that swaps between implicit, explicit, and semi-explicit methods. It's very complicated to always get you like a stable solution that kind of makes sense. That's what's nice about it. Whereas if you're kind of implementing this your own, you have tremendous power and flexibility in doing what you want to do, but you also have to think about all of these things. Suddenly, once you jump to an implicit solver, you gotta have a nonlinear solver within your solver routine. Okay. So you need to understand how this works. Okay, you need to understand. You know how to do nonlinear equations, right? We spent a lot of time on that chapter. All we're adding here, we're adding a nonlinear solver to an ODE integrator. Okay, so the additional knowledge you need to own here is how to discretize the ODE to make it to turn it into this nonlinear equation that you have to solve over and over again. I think in your notebook, let's see, in your notebook, okay, I have a backward Euler method implemented over here. Okay, and it also takes the right-hand side initial condition and time and a time step size. But then as I'm looping, you see this fsolve over here. That's where I'm doing the nonlinear solve for the residual function. Now, the backward Euler residual is very simple. It's defined as phi n+1 minus phi n minus delta t right-hand side at phi n+1 and tn+1. So, you know, the arguments get a little bit complicated. Again, I'm not going to ask you in the homework to use the code to do this. You can use ODEint in all your homework, and that's fine. You know, that's great. But I am asking you you will be responsible for understanding how the backward Euler method work, how implicit methods work, okay, and why you get a nonlinear equation, okay, for implicit methods, and how you would approach to solve it, because you know how to solve nonlinear equations. Okay. Yes. Oh, it's in your notebook. You don't see it? You don't have it? Oh, okay, I'm sorry. This is all question marks. Okay, I will upload even the BE residual. Yep, because we used to do this in class in the past. and that didn't go very well. So I mean, the only reason I'm teaching implicit methods is just to expose you to the idea, okay, just ever so slightly, how all of these things come together. Not like you're faced with a new problem. Well, you know how to do nonlinear equations, right? So you can combine nonlinear equations with the time integrator. Well, thank you for telling me about that. I'll upload the this notebook. Okay, I'll upload this notebook, and you're welcome to use this routine in your studies, whatnot. But ODEint should be sufficient. Okay, you really don't need that. You're not responsible for coding the backward Euler. Okay, but I know some of you are just interested in coding, so I'm happy to engage with you on the code during like student hours and outside class. Okay. All right. With that, I'm done for the day. We'll start on boundary value problems on Tuesday. I will assign a homework for initial value problems today. In that homework, you are welcome to use whatever routine we developed in class, including ODEint. Okay. If I were you, I'll just use ODEint and call it a day and focus on the interpretation of the results. Okay. You are still welcome to send me your improved pandemic model with social distancing. I had a few emails, and so if you're still kind of interested, please send them to me kind of just before, maybe by tomorrow or Saturday, and then we can talk about kind of what we can do with that. Okay. Thank you and have a nice weekend. Any questions on Zoom?
Nope. Thank you very much. Have a great day.
All right. Thanks, Nathan. Bye.